Hi, I'm MONZIM. Welcome to today's episode of the podcast, where we dive into the fascinating world of technology and its applications. Today, we're exploring the innovative UCAM Cloud, a real-time seat board system designed for universities, specifically aimed at making the intense section selection process smoother for students. Imagine this: a university with tens of thousands of students, and 3 times a year, a selection window opens. For the first few minutes, the system faces about 15,000 requests per second as students scramble to secure their seats. The challenge was clear: allow students to pick a section without the risk of double booking. However, nobody had requested a feature that shows live seat availability. That's where the real-time seat board came into play. I envisioned a solution that would allow students to see live updates on seat availability as they made their selections. The main guiding principle was straightforward. The real-time server needed to be a spectator. If it experienced issues, whether it crashed, was misconfigured, or faced deployment problems, section selection should remain unaffected. This meant no lost seats and no added delays in the selection process. To achieve this, several design constraints were established. First, there would be zero coupling to the selection path. The selection handler could notify the real-time system of changes, but it couldn't wait for confirmation or fail due to any issues in that system. Second, there would be no business logic or data persistence in the real-time server. It wouldn't manage seat allocations or write to databases. It simply displayed the state it received. Third, the system needed to be cost-effective during idle times. For about 360 days a year, when no selection window was open, the system should cost very little to maintain. Lastly, it had to handle a reconnect storm when the selection window opened. With thousands of browsers connecting simultaneously, the server needed to hold strong. Now, let's look at the architecture. It consists of 4 main components and a single direction of data flow. First, the Selection API publishes a snapshot of seat changes to a data store called Redis, after confirming the seat has been reserved. A long-running Go server subscribes to those Redis channels, maintaining an in-memory representation of the current state and sending updates to WebSocket clients at fixed intervals. An analytics worker also listens to this data stream to track usage metrics. The key to this design is the fire and forget approach. Once a seat is reserved and a response is sent to the student, the system publishes the update to Redis without waiting for confirmation that it has been successfully processed. This ensures that the selection process remains quick and responsive, even if the real-time server encounters issues. Instead of being an event forwarder, the hub acts as a renderer. It generates a complete snapshot of the current state of seat availability every 200 milliseconds, rather than sending individual updates. This approach allows for coalescing, meaning if a section changes multiple times quickly, only the final state is sent to clients. It also provides self-healing capabilities, since clients that miss an update will receive the complete state in the next refresh. Additionally, we incorporated a way to show how many students were viewing each section. This was accomplished using a Redis sorted set, which allows us to keep track of unique users without the need for a centralized coordination service. When students view a course, their user ID is added to this set with an expiry time. When a student's session ends or they disconnect, their entry is automatically removed after a set period. When it comes to handling connection storms, we implemented several layers of protection at the front door of the server. These include an accept token bucket to limit the rate of new connections, a hard cap on the number of simultaneous connections, and a graceful drain process to spread out the load during the deployment. The analytics worker, which operates separately from the real-time server, samples data from the seat updates and viewer counts to create historical records. This worker is designed to be stateless and idles between selection windows, ensuring it only runs when necessary. Now let's touch on the cost of maintaining this system. The entire setup runs on a single shared server instance, which is capable of handling both production and development environments. It's designed to scale down during idle periods, costing only a few dollars a month when not in use. Of course, there are trade-offs. For instance, viewer counts are maintained on a per-node basis, which could complicate things if the system needed to scale horizontally in the future. Additionally, the real-time board can experience a slight delay, up to 200 milliseconds, but this is generally acceptable for a seat selection system. In summary, here are 3 key takeaways from this project. First, make non-essential features cheap to ignore, ensuring that the core system remains robust and unaffected by any additional components. Second, render complete state snapshots instead of forwarding event updates, which allows for a more resilient and efficient system. Lastly, leverage time-to-live values for cleanup processes, simplifying the design and management of data. The real-time seat board is a testament to how thoughtful design can enhance user experience, without compromising the core functionality of a critical system. It shows that sometimes, the best way to add a feature is to build it in a way that it doesn't impact the essential services. Thank you for tuning in today. If you're interested in learning more about technology innovations like this, be sure to subscribe and explore our archives for more engaging content.